All right, last time we started section 1.3, and we finished up to the point of talking about rationalizing numerators, right? And so we were looking at limits. One of the basic things in general that we learned from all these properties of limits is that when you don't have 0 in the denominator, you can simply evaluate the function at the number you're given for x, right? And that's really good. And then when you do end up with 0 in the denominator and the numerator, there's some sort of factoring that can happen. Sometimes it's basic factoring that you'll remember, like these right here from like a calculus or a pre-calculus or algebra kind of course that you've had before. And then we encountered this one that you might not have seen anything like it before at all, where we rationalized the numerator. Things still sort of drop out in a very nice way, and we're allowed to then plug in the value for x. So we want to look at another component of these types of limits. The title of our section was limits, how do they describe it? Finding limits analytically. Analytically means the same thing as algebraically, so you will definitely hear me use those words interchangeably. And we're not just doing things that you would have seen in algebra, but also what you would have seen in a trigonometry class. So these are the limits of trig functions, and very much like the limits of algebra functions, they behave very nicely. As long as I plug the number in and I can get a value, right, it doesn't sort of make some kind of a denominator value 0, then I just get to plug the number in, right? I get to evaluate it. So the limit of sine of x as x approaches c is sine c. Cosine of x is cosine of c, and so on all the way down. There is this note up here at the top that says that c is in the domain. I do hope you sort of remember that there are some of these functions that have asymptotes. So if it's an asymptote location, then the point would not be in the domain, and you would not be able to simply plug the number in. So there are some values that do not work, even though you see no denominators actually written here. But they still are not valid for the domain. Okay, and then there are two that are special trig limits. And I have to sort of just give them to you, and right now you're just going to have to go on faith that they're true, because I'm not going to justify why they work. We don't have the tools yet to justify this, but we are going to utilize them when it comes available to be utilized. You'll notice that these are special because if you did try to simply plug the 0 in these cases, you'd get zeros in denominators, and that's a problem. But interestingly enough, you'd also get a 0 in the numerator. So this idea of 0 over 0 is sort of cropping itself back up again. And in this case, for these specific trig limits, they are going to equal 1 and 0 respectively. You're just going to take it on faith for the moment. All right, so we're going to go through a few of these. The directions say to find the limit of the trig function, and then in parentheses it says if it exists. Okay, so there is a possibility when we're working with some that they don't exist. The don't exist would be something that's going to end up being an asymptote. It's one of those values that I mentioned earlier. So if you try to plug these in, that's the right approach. So we're going to attempt to take the sine of pi times 2 over 2. And we're going to do a little bit of algebra and trig simplification to do this. So of course my 2's will eliminate. They will cancel one another out. And then I have to find the sine of pi. So this is a really good time to remind you that once upon a time you learned something, at least I really hope you did, called the unit circle. Some of you are nodding and some of you are looking at me like, unit circle, what is that? Oh dear. All right, so I want you to put a note to yourself in your to-do list or something that says Google, search, internet, whatever, unit circle, and print one off. Because if it's been a little bit since you've looked at it, you're probably going to need to memorize portions of it at least again, because you're going to utilize it. And for right now, you don't really need to memorize it. Just print it out and use it in your homework for the next couple of assignments. But by Friday, when you take the quiz that will include or potentially include something with trig, you need to remember a little bit about your unit circle. Now, sometimes your calculator can help you to keep that into your memory, right? In the sense that we could take this one right here and we could just use our calculator to evaluate it. And it would work really nicely. There's one in your book. That's even better. Thank you so much. What page is it on?
It is, it's not like a page. It's like in the very front, and it's with all the...
Okay, so in one of the chart sections in the front of your book, it looks like Elisa said that there's a unit circle that you could use in there. So if you don't want to grab it from there, grab it from your loose leaf book, and you can stick it in your notes. That'll work great. Thank you, Lisa. This one, sine pi, is actually very friendly, and if your calculator is there and you can utilize it, it's great. So does anybody remember what sine pi is, or you've already plugged it in your calculator?
0.
It's 0. So the sine of pi is 0, and that works really nice. So why did I say that one worked really nice, and maybe some others do not? Well, because if you remember, some of your unit circle values have radicals, right? And your calculator does not take a decimal expression and turn it back into a radical. That's just not a function of the calculator. If somebody wants to create one like that, I'm sure you will make a mint. But so far, I haven't seen one created that does that. So some of you are like, wait a minute, that sounds like a money-making opportunity to me. So I will leave that in your court. And the next one is an example of one such thing, function like that. Right? I can definitely find the cosine of this value, which is 5 pi over 6. But my calculator is not super helpful. And so just for the sake of just trying it out, go ahead and put it in. Tell your calculator cosine of 5 pi over 6. And if you do, your calculator will give you an approximation like this. And of course, it keeps going after that. So if that's the answer you give me on your quiz or homework or something like that, and it didn't tell you to round, and it probably won't, then you've missed the mark, right? You haven't quite understood what we're going for, because most of the time in calculus, we're going for exact answers, precision, which means we want the radical version. And so there's a couple of things you can do. One option is that you could simply remember your unit circle pieces and how they're sort of related, the left-hand side and the right-hand side and how they mirror one another. Same thing for the bottom of the unit circle. The other thing that you could do is you could remind yourself how to use your calculator to help you remember, right? So like there's only 2 radicals that show up on the unit circle, square root 3 over 2 and square root 2 over 2, right? So you could remember which one of these it is, or you could use your calculator to help you remember as well, and that would be okay. So do you remember, or does somebody find which one this is?
Negative square root of 3 over 2.
Yeah, it is. It's negative square root of 3 over 2. And again, if you wanted to see and you weren't sure in your calculator, you could just say, okay, I think it's the radical 3 over 2 one. Put it in your calculator, see if the decimal matches. That's an option. So I'm not super specific on how you need to get there, but we do want our answers to be exact, and this is the exact expression we're looking for. Okay, so that's what happens when you're just able to directly evaluate into them, right? You're thinking unit circle kind of stuff. Over here, directions are the same, but what you see happening is the inability to evaluate by plugging the number in. Okay? Yeah. If I try on the first one, if I even forget and I try on the first one, I'll end up with 0 over 0, and I should have a red flag that says, now wait a minute. That's not okay. Something's going on here. If it were algebra, I'd try to factor it and see what would happen, but it's trig, so now what do I do? Well, over here, I gave you a couple of very cool facts, right? Things that we can utilize. The first one's the one that's most like what I'm dealing with because it has sine in it. So this one over here also has sine in it. So what does it look like to do this particular value? It looks something like this. This 5 right here is a constant. Agreed? And we had a fact, it was earlier, like what we did last Friday, over here, let me find it because I want to tell you that I'm not just making it up, that said that if there is a number, a constant multiplier, or a scalar that's being multiplied at, I have the ability to pull it out in front of my limit. It's a multiplication fact, right? When it's a constant. I'm going to use that right here. I'm going to pull that 5, which is in the denominator, so it's really a 1/5 out in front. And then I'm going to write the limit as x approaches 0 of the sine of x over x. And lo and behold, this looks exactly like one of the facts that I gave you. What's that limit? 1. This is 1/5 times 1. You don't necessarily have to write that down, but that's what it is. This limit's 1/5. I do expect to see this with the 1/5 pulled in front, separated. Okay? I don't have you show a whole lot of things like that, but I expect to see it here, right? 1/5 pulled in front, and then the limit, and then you can jump to the end if you wish that it's 1/5. Number 9. So, if you go out on Canvas, there is a very brief document you're welcome to print off if you'd like, or just transcribe it on your own paper. And they're Trig Identities. So there's really only 3 Trig Identities we need for calculus. We need the Quotient Identities. Quotient Identities tell you like that tangent is sine over cosine, and cotangent is cosine over sine. We need Reciprocal Identities. Reciprocal Identities tell you that sine is the reciprocal of cosecant, that secant is the reciprocal of cosine, and that cotangent is the reciprocal of tangent. And we need the Pythagorean Identities. Pythagorean Identities tell you that sine squared plus cosine squared is equal to 1, and there are similar statements for tangent squared and for secant squared. Okay? So feel free to print that off or to copy that. You'll need them from time to time. You don't need them all the time, but when you need them, it's nice to have them and not have to sort of just all of a sudden, be lost as to what we're looking at. So as you're taking a look at this one, this does not look like either of the ones that I gave you a special value for. But I do have 2 trig functions on top, cosine and tangent. And so I need to have the ability to manipulate them to see if I can change one or both of them to evaluate and eliminate anything in common. And in particular, the one that's most useful here is the quotient identity for tangent, because the tangent is the same as the sine of x over the cosine of x. All that's divided by x. And what do you see happening then on top? Yeah, I can cancel out or reduce or eliminate the cosines. So I'm left with the limit as x approaches 0 of sine of x over x. And we've encountered that once before. Even on the screen, that limit is 1. So you may have some places where you have a little bit of trig simplification. Any questions? All right.